Yeah, but then when you watch online, if there's like that one little question that you just want to ask, you can't.
Yeah, but I see your methods.
Yeah, you do. All right, let's just continue then. Well, we'll start with a recap first. Remind us what topology is, because there's nothing intuitive about what topology is. You just have to memorize the definition, get comfortable with the definition. That's the only way you're going to understand what a topology is. So let's make sure that we understand what it is, review it from last time, the exact same definition. So let X be any set. A topology tau on X is a collection of subsets of X such that three things hold. 1, the empty set is in tau and X is in tau. 2, well, do you remember what we called the members of tau? We had a special name for those sets.
Like the elements of tau?
Yeah. Open sets. So we don't have to keep saying this inside the topology, we just call it an open set, so it'll make it easier for me to explain this if I can use that terminology. So 1, we require the empty set and this entire set X to be open sets. 2, if you have a collection of finitely many sets, finitely many open sets, then their intersection has to also be an open set. So the intersection of finitely many open sets is open, is another way that you could say number 2. So the intersection from I going from 1 to n of some collection of subsets a sub I, where each a sub I is open. Oh, they were coming. Is it just you? All right. Well, Rhoda seemed pretty not into it last time, so not surprised there. Okay, so the empty set and the entire set are open. If you have a finite collection of open sets, their intersection is also open. And then any arbitrary union of open sets is open. This can be infinitely many, this can be finitely many. So the empty set and the entire set are open, any finite intersection of open sets is open, and then any arbitrary union of open sets is open. If that's the case, if tau is a collection of sets that satisfy those three rules, then tau is a topology. This is recap from last time. Now, there were some basic topologies that we're going to keep mentioning as examples in this class over and over again, so I want to make sure you remember them. First one was called the trivial topology, the smallest possible topology you can make. The trivial topology was just the entire set and the empty set. Right? It satisfies this one, and then it vacuously satisfies these ones. Not vacuously, but the intersection of this and this is just the empty set as that, and the union of this and this is just the entire set that. So, we're done. The second topology that we talked about was a discrete topology. Remember what I mean by this fancy P of X?
Mm-hmm.
The power set. What's the power set of X?
It's
All the subsets of X.
It's the set of all possible subsets of X. Make sense? Okay. So that topology, you think about that as like the biggest topology that you could possibly make, including every possible subset that you can. We call that the discrete topology. And then we introduce this notion of one topology being finer than another topology, or one topology being coarser than another topology. So if I have two topologies, tau 1 and tau 2, which one of those is finer? Tau 2 is the finer one. Tau 1 has all the breakups that tau 2 has all the breakups that tau 1 has, and possibly more. So tau 2 is finer than tau 1, tau 1 is coarser than tau 2. If you think about it in terms of these two sets, this is a subset of this. This is very fine. We break the open sets down to their individual elements. This is very coarse. We've only got two open sets, everything or nothing. So this is a subset of this. This is the finer one. This is the coarser one. And then we call it strictly finer or strictly coarser if it's a proper subset. Good there? Okay. And then the big theorem that we did last time was theorem 1.4. So let X be a topological space and let A be any subset of X. What did we prove? We proved that A is open if and only if for every element in A there exists some open set containing that element that's a subset of A. So a set A is open. Maybe draw a picture of it. So here's A. A is open if and only if for every point in A you pick, we pick one, there's X, there exists some open set containing that point where the open set is also a subset of A. It could be A itself or some smaller set, right?
Okay.
So A is an open set if and only if it satisfies its property. Terminology, if I have an open set that contains X, then this set is a what of X? Do you remember the special name for a set like that? Neighborhood.
Oh, yeah.
It's a neighborhood of X. So when you see U sub X, we usually read that as a neighborhood of X. Open set containing X or neighborhood of X, same thing. I'll probably accidentally say neighborhood of X over and over again, so make sure that terminology is clear as well. So this is kind of a high level, everything that we covered last time. Anything there that feels fuzzy, that you feel like we need to recap or talk about more before we continue?
Can you go over the rules for topology this one?
Yes, the rules for a topology. So you give me some set X. We'll look at, try to use the room up here. We'll look at X equal to the set AB. So then we got some tau. We'll make tau equal to the empty set, the set containing A, and the set containing AB. Is tau a topology on X? We need to check three things. One, do we have the empty set and the entire set X in tau? Yes, right there and right there. Two, pick any finite number of sets in tau. Is their intersection also in tau? In this case, yes. Intersect all three of them, you get the empty set. Intersect these two, you get A. Intersect these two, intersect anything with the empty set, you obviously get the empty set. Intersect this, intersect these two, and you just get A, which is also in there. Yes. Okay, third criterion. Is the union of any arbitrary collection of open sets open? If I pick any arbitrary collection, pick any open sets I want, union them up, is the result an open set? In this case, yes it is. Okay, so tau is a topology on X. Does that example help? The rules make sense? Any other questions? All right, then let's move on to a basis for a topology. So it's really tedious to have to try and write out all the members in a topology, especially when we're talking about infinite sets. And so the idea of a basis is there some small number of sets I can pick out of that topology that somehow represent the topology. And all we have to do is keep track of some smaller set of basis sets. And so the idea behind a basis element is basis elements are open sets, and any set you can take by unioning together basis elements is also an open set, and that's how you create your topology. I don't know, try and come up with an analogy. Think about like Lego. And we wanted our open set to be all possible constructions you can make with Lego. Imagine trying to enumerate that set. That would be a nightmare. But we could go and we could identify all the possible Lego pieces that there are. There's a finite number of Lego pieces, right? So go count up all the possible different Lego pieces that there are. Say these are basis elements for structures of Lego. So the little individual Legos themselves are considered Lego structures, and then any combination of them you choose is also a Lego structure. That's what we mean by Lego structures. Similar thing here. Rather than listing out all the open sets, we're going to list out basis elements. We're going to say all these basis elements are open, and then any union of basis elements is also open. And that's how you get all your open sets. And the big theorem is going to be to prove that a basis does in fact give us a topology. So that's big idea what this section's all about. So now let's jump into it. Basis for topology, definition 1.5. Let X be a set and let beta be a collection of subsets of X. Let me know if you get mixed up between my betas and my B's. I'm always going to use B to be a member of beta. So beta is going to be a collection of sets, and B is always just going to be a set of elements in X. So that's how I'm going to use those. So let X be a set and let beta be a collection of subsets of X. Then beta is a basis for a topology on X if and only if it satisfies these two rules. 1. For every point in X, there is a basis element containing that point. Okay? 2. If you have two basis elements such that X is in their intersection, then there has to be a third basis element such that X is in that third basis element and it's a subset of their intersection. So if I have B1's this set here and B2's this set here, so if these two are basis elements, and X, this point here, is in their intersection, then there has to be a third basis element B3, such that X is in B3, and B3 is a subset of the intersection of B1 and B2. Once again, it should not be obvious or intuitive to you that, oh yeah, that makes sense for a basis. It's not necessarily intuitive. It's one of those things that you just need to understand the definition, start using it in proofs, and then some intuition gets developed along the way. So, if you say, why is that the way that it is? Because it happens that this way works. All right. But any question about what these two are saying?
Your picture is nice, but so a basis is pretty much the next big thing up next to a point, right? You're saying
A
that's
basis is a subset of X. So X is the whole set.
okay.
For each, so using pictures to help us see it, for every point in X, so pick any point in big X you want. So this is big X, this set. Pick any point little x you want. There has to be some element in beta, some subset of X that's in beta that contains that point. That's criterion 1. That's this. 2 is that if X happens to be in the intersection of two basis elements, then there has to be a third basis element containing it, such that that third basis element is a subset of the intersection of the two basis elements. Does that make sense?
Just to clarify, with your definition, you're given a topology, and then you're choosing a basis.
No, we're given a topology. We're going to use this beta to construct a topology. We're talking about it as though it gives a topology, even though we haven't shown that it gives a topology yet. We're talking about what it means for it to generate a topology. But we're going to use this beta to construct some topology.
But don't you get the beta from a topology because it's a specific basis for a specific?
No. We do not get the beta from a topology. The beta gives us a topology. So I know that it's ugly in how the author is introducing this because he says beta is a basis for a topology on X, and you're wondering what topology? We don't know. Some topology. We've yet to discover what exactly this topology is. I haven't proven to you that beta gives us a topology. We wouldn't even know how to do that yet based off of what we have. But if beta satisfies these two rules for some set X, then it is a basis for some topology. And later we'll see exactly what that topology is.
So you're just saying if a set satisfies, if beta satisfies these conditions, then there exists a topology out there.
That we can generate from beta. And we've yet to say what it means to generate it from beta, and then we're going to prove that what it generates is a topology.
Okay.
So if after we covered the generate part and you're still unclear, then let's go over it again.
All right.
Okay. I might accidentally, so put this note here in case I accidentally do it and don't specifically say. The members of beta we call basis elements. Beta is a basis. We call the things in beta basis elements. What are the basis elements? They're subsets of X, right? So try and keep that straight in your head. Beta is a collection of subsets of X. Beta's elements, or basis elements, are subsets of X, and not the individual elements of X. Even though we're going to call them basis elements. Okay, so good with what a basis element is and that terminology? It's basically just my B's. Alright, so let's look at an example of a basis real quick. A very famous one on the real numbers. So on R, the set of all real numbers, let beta be the set of all open intervals. What's the open interval AB? What points are in there?
A, B, except not including A, not including B.
All the numbers greater than A and less than B. That's what the open interval AB is. So if we have if I have an open interval, so here's A on the number line, here's B. If we're talking about A, B open interval, that's all these points.
Okay.
Open interval. So let beta be the set of all open intervals. We're going to show that beta is a basis for a topology on the real numbers. So we need to show two things. We need to show that for every real number, it's inside a basis element. And then we need to show that if a number is inside the intersection of two basis elements, then there's a third basis element containing that real number, where that third basis element is a subset of the intersection of the two basis elements. So we'll start with this one. We need to prove for every real number there exists a basis element containing that real number. So we need to show that for every real number, I can find an open interval containing that real number. So this one. Observe that for any real number you pick, x is inside the open interval, x minus 1, x plus 1. Right? Nice and simple, nothing weird there. Okay, so we showed the first condition. Now we need to show the second condition. So let A, B, and C, D be two open intervals, and let x be something in their intersection. You with me so far?
Yeah.
We have two open intervals. What might this look like? A, B is that open interval, C, D is that open interval, x is somewhere in their intersection.
Gotcha.
Okay. Let x1 be the max of A and C, the left-hand elements, and let x2 be the minimum of B and D, the right-hand elements. Then this is going to be an open interval containing x, and it's going to be a subset of the intersection because it's going to be the intersection. So draw a picture how we're saying this real quick. So we've got, here's my open interval AB, here's my open interval CD, and I know that x is in the intersection. I say, take the bigger of A and C, call it x1, in this case that's C. Take the smaller of B and D, call that x2, in this case that's B. Then x is going to be between x1 and x2, right?
Mm-hmm.
And x1 and x2 is going to be a subset of the intersection because it is the intersection. Right?
Oh, okay.
But what if there is no intersection?
Then it's vacuously true. If this is true, then this is true. If this is never true, then the implication is vacuously true. And you still have a basis. So no intersections means, yep, we're good. Or if the intersection always has a subset that's a basis element, we're good. And it's not going to be that uncommon that the intersection itself gives us a basis element like it did in this case. Good? Okay. Let's move on to another example. We're going to let beta be be the collection of all singleton sets for every element in X.
Singleton set?
Singleton meaning it only contains one element.
Okay.
As a single element. So for everything in X, grab it out of X, put it in a set, put it in beta. That's what we're doing. We're going to show that this is a basis. This one's a lot more straightforward. Observe that for everything in X, X is in the set containing X, which is in beta. So every X is in a basis element, the set containing it.
Yeah.
Right? Because how do we get our basis elements? We take everything in X and we just stick it in a set. Pick one thing out of X, put it in a set. Pick one thing out of X, put it in a set. That's what we're doing over and over again to create beta, right?
Mm-hmm.
Okay. So 1, obviously true, right?
Yeah.
2 is going to be vacuously true. Because if I have 2 singleton sets that aren't the same set, then their intersection, they don't have one. I can't have 2 singleton sets intersect unless they're really the same set, in which case I don't have 2 sets. I have 1 set.
Right.
Right? So this condition, vacuously true. Or this one vacuously true because we never have this. Make sense?
Mm-hmm.
Okay. Or if you want to think about these 2 sets can be the same, then anytime they intersect each other, they have to be the same set, in which case it's obviously true that way too. So however you want to think about it. Either way, that's definitely a basis, right?
Mm-hmm.
For any set X you want, where X isn't empty. Probably should have specified that. Where X is not equal to the empty set. Okay, So now, we've talked about some examples of a basis. Now we're going to talk about what it means for a basis to generate a topology. So we know now what a basis is. Now how does that generate a topology? What's the topology it generates? So let beta be a basis on X. Then the topology tau, generated by beta, is obtained by defining the open sets, or the members of tau, by defining the open sets of tau to be the empty set, and every set that is equal to or a union of basis elements. So what's in tau? The empty set, everything in beta, and everything you can get by unioning elements in beta. That's what's in tau.
Right.
So if you put all those sets in tau, what you're left with is a topology, and we're going to prove that what you're left with is in fact a topology. But this is what we meant by the topology generated by beta. So now, come back and look at this one real quick, and let's make sure these two make sense. Let X be a set and let beta be a collection of subsets of X. Then beta is a basis for a topology on X if and only if these conditions are satisfied. And then what topology does it give us on X? It gives us the topology containing the empty set, everything in beta, and everything that's a union of things in beta. And now we need to prove that this tau is in fact a topology. That's what remains to show, right?
Okay.
Anything weird?
Yeah. I don't, so in order for it to be a topology, it has to be everything in some set X.
We need to show, so what you should know how to do now is A, identify whether or not something is a basis. That's using this. B, identify if a set can be generated by the basis from this. What does it mean to be generated by the basis? It either needs to be the empty set, a basis element, or a union of basis elements.
Does it need to have all of
Now
those?
we need to prove that all the sets that you can get this way, in fact, give us a topology. That's the one thing we haven't shown yet.
But you have to have
Oh.
one of those, not all of them.
Yeah, you need to meet one of 3. Okay, that's a good point. Over here, you have to meet both the conditions. When I'm talking about what are the open sets here, we're ORing 3 conditions together. You need to either A, be empty. If you're empty, you're an open set, we're good. B, you need to be a basis element. If you're a basis element, we're good. You're in tau. Or C, you need to be a union of basis elements. If you're a union of basis elements, you're in tau.
Okay.
So all the possible sets that you can create that way are what we're saying is going to be a topology.
So you're saying that the empty set can be a topology by itself?
No.
Oh.
The smallest possible topology you could have is this.
Okay.
Any other questions? Or maybe just look at some examples and come back to questions. So, example 1.7, let beta be the set of all singleton subsets of X, where X is some non-empty set. Then what is a topology generated by beta? It's a discrete topology. Notice that pick any subset of X you want. One of three things is true. Is the empty set? It's just one element of X, or it's several elements of X, which could then be represented as the union of all their singleton sets. Is that making sense, or do we need a concrete example?
That is not
Concrete example, okay. Let's put C there. Okay, concrete example. So X is equal to, we'll say, A, B, C, D. And I'm saying that if beta is this basis, what's beta in this example? The set containing the set A, B, C, and D, right?
Yeah.
That's what beta is.
Mm-hmm.
Now I'm saying pick any subset of this you want, A, B, C. Is this just a union of basis elements? Yes, it's the
Yeah.
union of A, or the set containing A with the set containing B with the set containing C. Right?
And you're saying this, so you're saying beta can generate the discrete topology?
The topology generated by beta is the discrete topology. If you take all the sets that are either A, empty, B, these sets, or C, unions of these sets, you just created all the possible subsets of X, the discrete topology.
Okay.
But you'd have to take all of those to create the discrete topology.
Correct. Any set that satisfies one of those three conditions is open, is in our topology.
Okay, wait, so you said that, I'm just confused because
You're not saying ABC is the discrete
in
topology
order
in
to
that
create
case.
the topology,
No.
then you have to have it.
This was a set in the topology.
Okay.
What's in the topology? So tau is equal to, okay, the empty set's in there by definition,
Yeah.
right?
Yeah,
All of these sets are in there by definition. We won't write those.
yeah,
What about the set AB? Is that in there?
yes,
Is it?
yeah.
How do you know? Because it's a union of the set A with the set B, which are both basis elements. What about the
so
set
it's
ABC?
all those conditions, not just one of them.
If it satisfies any one of them, then it's in tau. This set satisfied one of them, it's the empty set, so it's in tau. The set A, the set containing A satisfied one of them, it's in beta. The set ABC satisfied one of them, it's a union of basis elements. If the set is either empty, a basis element, or, we're oring those together, maybe you say it with all the ors. If the set is empty, or it's a basis element, or it's a union of basis elements, then it's in the topology, generated by beta. What do we mean by the topology generated by beta? We mean all the sets that are either empty, or basis elements, or a union of basis elements.
Okay, I thought you were saying that what has to be in the basis element, in beta, were all three of those things.
Oh no, that's not what's in beta.
Yeah, but it's
Beta
actually,
is, in this
it's
case,
in
is just a singleton
the
element.
topology.
Huh?
But it's in the topology.
Yes. We're talking about what sets are in the topology when beta is this.
Okay, that's what I was confused.
Okay, good. Make sure it's all clear. So we understand that if beta is this, then our topology is a power set on X. That makes sense?
Yeah.
Anything weird? You good?
Yeah.
Okay. Let's look at another example. Might need some of the space to scribble. The topology on R. So let R be the real numbers and let beta be all possible open intervals. With me so far?
Okay.
Then the topology generated by beta, we call that the standard topology on R. And for those of you in calculus, you'll see that this is what we're always, well, I'll explain it when it comes up in calculus, so you see it here. Anyways, so question. Is this set open?
Yeah.
Yeah.
How do you know?
Because 0.5 is in the interval. On the real numbers, this is an interval.
Yeah,
because-
0.5 is in there.
Yeah.
How does that tell me that this is open?
It doesn't.
Parentheses.
Because there's parentheses, and so it doesn't
Yeah.
include the endpoints, and so it's an open interval.
Well-
But how do we know it's an open set in this topology?
I don't know. Isn't it because it satisfies the conditions of beta?
It's a member of beta. What is beta? The set of all possible open intervals. Is this an open interval?
Yeah.
Yes.
Then it's an open set. We gotta check one of three things. U equals the empty set, U is in beta, or U is equal to the union of B sub alpha, some set B sub alpha where each B sub alpha is in beta, something like that. U either has to be the empty set, it has to be in
Wait,
beta, or it has to be a union of elements which are in beta. Then U is open, if it satisfies one of these. This, or this, or this.
So you're asking if that was open?
Yes, is this set open in this topology? Yes, because it's in beta,
Oh.
right?
Yeah.
Okay.
What's a standard topology?
The topology that is generated by this basis is what we mean by the standard topology. So from here on out, when I say, look at R with the standard topology, then you're going to think in your head, okay, that's the topology that I can generate with all possible open intervals.
So you don't know what that topology is, you just know it's the topology generated by all open intervals.
We know what the topology is now, we just haven't proved that's actually topology. You know everything that's in this now. So for example, is this in it? Let's do 0 to 97 unioned with 13 to, I don't know, 21.
Yeah.
Yeah? How do you know?
Because both of those are in beta, and so and then the union.
Yeah, you say this is a basis element and this is a basis element. Therefore,
The union of them.
their union has to be an open set. Or you could say the union of those two things is really just this, and this is in beta. So this set that we're talking about here is a member of beta. Therefore, it's an open set. Let's look at another one. Is that open?
Yeah.
Yeah.
It has to be.
How do you know?
It's
It's the union
the
of
union
beta.
of all of the.
Of all of beta?
Yeah.
Union of all of beta? Yes, that works. We could be a little bit well, we could also just call that an open interval if we wanted. We could also say for all x in R, call u sub x equal to the open interval x minus 1 to x plus 1. Then the union for all x in R of u sub x is equal to R. Tons of ways we can do it. We're going to see stuff where we do it like this, so I want you to make sure that this actually makes sense. Don't think I already understand it, so I'm going to ignore this way of thinking about it.
I don't understand that.
So we're going to take for every number in R, we're going to look at the open interval around x. So when x is right here, we're taking this open interval. And when x is right here, we're taking this open interval. And when x is right here, we're taking this open interval. And keep unioning up all those open intervals for every x in R.
Then
And you'll be left with all the real numbers.
Oh, okay.
Because for every real number, it's obviously in this open set. And then for any, for any member in this open set, it's going to be a real number. Therefore, the sets are equal. Okay, so there's another way that you can think about it. Let's try to get a little bit trickier with you. Let's do R minus the point 1. Is that an open set? All of R except 1.
Yeah.
Yeah? How do you know?
I don't know.
That's definitely not an interval now.
It's the union of two.
Yeah, what do we have? We have negative infinity to 1, union with 1 to infinity. That's an open set, that's an open set. Therefore, that's a union of basis elements. That's a union of basis elements. Union them together, still just a union of basis elements. Is that open? Is there some number, even if I do like an infinite union?
No.
No, it's not. Wonderful. See? So you already know the standard topology on R. I haven't proven that's a topology yet, but you know what sets are in there.
Okay.
Maybe try another one. What about the set just containing 1?
No.
No, that's definitely not an open interval, and there's no way I can get that by unioning up open intervals. Right? Because unioning can only make it bigger, and every open interval has how many elements in it? At least 10. That only has 1. It's good when you smile. It means you're paying attention. Alright. So just smile every time it sounds like I'm trying to make a joke. I'll think you're paying attention.
Sort of,
Alright. Any questions here before I move the camera? Because we're to the squiggly. Okay, I'm going to move the camera and we'll continue. Make sure we got the whole proof. Okay. Peter, can you see that camera?
I can try it.
Am I still on?
Barely. I can see your hand.
So that's roughly what we got?
Yeah.
Wonderful. Thanks. Okay. So now, the next big proof is obviously, so we know what a basis is, we know the topology that a basis generates, but is it in fact a topology? That's what remains to show. So let's prove what it generates is in fact a topology. Before we get to that proof, we need a little lemma that we're going to use. You remember what we typically mean by lemma?
Yeah.
It's a little helper proof. It's not the crux of what we're talking about. It's just something that we need to do along the way. We could have done it inside our proof, but to help keep our main proof clean, we do it separate and then go back to our main theorem. So our lemma. Let beta be a basis and let B1 to Bn be some finite number of basis elements. With me so far?
Yeah.
Okay. Oh, some finite number of basis elements such that x is in their intersection.
Of all the basis elements.
Yes. Not all the basis elements, but all the ones that we picked out.
Yeah, of your finite set.
Yeah, so beta could have infinite things in there. We picked n of them such that they have some point x in their intersection. We're going to prove then that there must exist some basis element b prime such that x is in b prime and b prime is a subset of that whole intersection.
Okay.
This is almost the exact same thing that we said when we talked about what it means to be a basis, right? We said a basis, if x is in the intersection of two things, then there has to be some third set, some third basis element, such that x is in that basis element, and that basis element is a subset of the intersection of those two basis elements. Now we're doing that, except for instead of just intersecting b1 and b2, we're intersecting b1, b2, b3, b4, b5, all the way up to bn. Now, I realized after I did this proof that proof by induction you haven't seen before, and some of you probably aren't that comfortable with.
Yep.
So, let's make sure that we understand the idea behind proof by induction. Here's the way that I always like to introduce it. I say, imagine I've got some secret set A. And I only tell you two things about A. I tell you, first off, the number 1 is in A. And I tell you, secondly, that if K is in A, that implies K plus 1 is in A. Okay, that's all you know about A. What things do you know are in A? What is for sure in A?
One.
1's in A.
Okay.
No, if K is in A, then K plus 1's in A.
Oh.
That's what we know.
Two is your-
All we know so far is 1's in A. But this says if 1's in A, then 2's in A, right?
Yeah.
Okay.
That's what we, maybe you're not used to the implication arrow. Right, this way. If K is in A for any number K, then K plus 1 is in A. So A has a special property that anytime K is some number in A, then whatever that number is plus 1 also has to be in A. So I know that 1's in A, and so since 1's in A, I know 2's in A. Right? And now since I know 2's in A, I know 3's in A.
Yeah.
And 4, and 5, and 6, da 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 da. So I know all the natural numbers starting at 1 are in A. Notice if I would have started this at 7, then what would you know about A?
7.
You would know that 7's in there, 8's in there, 9's in there, etc. All the natural numbers starting at this number. We usually refer to this number as the base case, just terminology. So that's the idea behind proof by induction for sets. Now we're not going to talk about for sets, we're going to say we're looking at all the numbers that make a statement true. In this particular proof, I'm going to show that 2 makes the statement true. And I'm going to show that if 2 makes a statement true, then 2 plus 1 makes, and if K makes a statement true, then K plus 1 makes a statement true. Therefore, what numbers make the statement true? The numbers that make the statement true are going to be 2, 3, 4, etc. Which is what we're going to want.
Why are you starting with
Because it's trivially true for the case of 1.
okay.
But so proof by induction, the idea is first off we're going to show that the statement is true for some base case, some initial number 2. Then we're going to show that if the statement is true for some natural number K, then it's true for K plus 1. We don't know anything about K except for that it's a natural number.
So does the author prove this by induction?
No, the author does this proof by induction, sorry. But we're not going to prove proof by induction in this class. The reason that we don't prove proof by induction in this class is one, topology is far enough along that it can be pretty safely assumed that if you're doing topology, you already understand proof by induction.
Really?
And, huh?
Is it really?
Topology is one of the most advanced math classes I've taken. Formally. So, yeah. And then the other reason is the axioms that you use to prove this aren't axioms that we're really interested in this class. So, for example, in discrete math, what's the axiom that we use to prove by induction?
It's proof. It's the
Proof by smallest counterexample, but how did we use proof by smallest counterexample? What's the axiom we relied on? The fundamental assumption? The well ordering principle. So we had to assume that every set of natural numbers has
right.
at least element,
Right.
and we ultimately use that assumption to prove proof by induction. In calculus, the way we do it is we start out with the completeness axiom, and we show that the completeness axiom implies proof by induction. So there's different ways that you can show that proof by induction is true. It depends on the axioms you're going to start with. Since the axioms that we would need to start with aren't axioms that we're really interested in this class, we're just using proof by induction without proving proof by induction works. So for proofs of it, you can see, I don't know if you want to see where I do that in discrete math, I can show you the lecture where I do that, or in calculus, I can show you the discrete math way is probably more intuitive. It very, very, very most likely is what I mean by probably. Like I would strongly recommend that one over the calculus one. Okay, so that's the idea behind proof by induction. That's what we're going to do here. We're going to show that this statement is true for 2, and then we're going to show that if the statement is true for k, then it's true for k plus 1. Therefore, it's true for all natural numbers starting at 2. And we already know trivially that it's true for the case where n equals 1, right?
I understand that why it's true for n equals 1, but like, why do we need to prove it's true for n equals 2 if we know it's true for n equals 1? Why not just go straight to let it be true for x and it's true for x plus 1?
Because we can't take an intersection when we just have 1. So I need to use, this is how I'm going to do my base case. I'm going to use this for my base case. And my base case is using 2 sets.
Oh, I see.
So it doesn't make sense to talk about the intersection of just one set, which is why we're starting at 2. So that's why it's obviously true in the case where it's 1, because it's factoriously true. But 1 isn't a natural number that satisfies the statement. Okay. So base case, for n equal 2, then, so we're talking about just b1 and b2. We only have 2 basis elements, and we know that x is in the intersection of those basis elements. By definition of a basis, if x is in the intersection of 2 basis elements, there has to exist some third basis element called b prime, such that x is in there, and that set is a subset of their intersection. So we know this by definition of a basis, right?
Yeah.
Any question about the base case? Okay, so now we need to show that the statement being true for k implies the statement is true for k plus 1. How do you prove an implication? You assume the antecedent, and you show that implies the conclusion, right? So assume the antecedent. Assume for n equal to some number k, that when you have x in the intersection of k basis elements, there exists some third basis element b prime, such that x is in b prime, and b prime is a subset of the intersection of those k basis elements. So we need to show that being true implies that it's true for k plus 1, right?
Yeah.
Okay, so then, if x is in the intersection of k plus 1 basis elements now, we need to show that this being true means that there exists some b prime, such that x is in b prime and b prime is a subset of this, right? So that's where we're going, and we need to use this information, the information we have up here, to do it. So, maybe let. So let x be in the intersection of k plus 1 basis elements now. Well, what does that mean? That means x is in the intersection of k basis elements intersected with a k plus 1th basis element,
Yes.
right? If it's in the intersection of k plus 1 things, it's in the intersection of k things intersected with one more thing, the k plus 1 thing.
Right, then that means there's another one.
So now we have x is in the intersection of two sets, right? The intersection of all these sets, that's just a set. So we have a set intersected with a set. And we know by definition of it being a basis, when you have x is in a set intersected with a set, oh, sorry. No. Forget that for a second. Since x is in both of these, since x is in the intersection of these two sets, then x is for sure in this set, right?
Yes.
So now we know for sure that x is in the intersection of k basis elements. Look at our assumption. Our assumption is that if x is in the intersection of k basis elements, there exists some third basis element such that x is in that third basis element and it's a subset. So since I know that x is in the intersection of k basis elements, then there must exist some basis element called b star such that x is in b star and b star is the intersection of k basis elements. You with me up to here?
Yeah. But I thought we've already said that.
Yeah, isn't it k plus 1 basis elements?
We're not done with the proof yet.
No, I'm saying
Oh.
I thought we already
We're
said that.
getting to this line. So x is in b star intersected with b of k plus 1, where what's b star? B star is the basis elements. That's the intersection of k basis elements containing x, where it's a subset of those, right?
Okay.
Yes. But didn't you already say that on line 2? With b prime.
With b prime? Yeah.
Yeah.
Line 2 is how I justify this.
Oh.
What am I ultimately, so
But
line
didn't you just
3,
say that it's just b
ignore everything that you see for line 3 for a second, and imagine that you were trying to prove this yourself. You know that you need to start out with x is in the intersection from I equals 1 to k plus 1, b sub i's. That's where you need to start, and you would know, where do I need to get? I need to get that there exists b prime such that x is in b prime is a subset of the intersection from I equals 1 to k plus 1 b sub I. So I know I need to get from this to this, and I know that I need to use this information on line 2 to do it. So I take the intersection of k plus 1 basis elements, split it into the intersection of k basis elements intersected with one more. Since x is in the intersection of those two things, x is in this thing.
Yes.
So since x is in the intersection of k basis elements, using line 2, there must exist some other basis element called b star, such that x is in b star is a subset of the intersection of those k basis elements, right? And since b star is a subset of this set, and x is in it, since x is, well, from here, this line, we knew that x was in b of k plus 1. Now we know x is in b star, therefore x is in b star intersected with b k plus 1, right?
But if b star is a subset of the intersection of all those.
B star is a subset of this thing. It's the basis element that is a subset of this thing.
How do we know that there exists an intersection between b
Yeah,
star
that's
and
what
b sub
I'm
k
wondering.
plus 1?
Let x be something in this intersection.
Oh, wait.
So you're.
Okay.
So x is in all these sets.
Okay.
B star, so x is in this set and this set for sure. Since x is in this set, we know that there exists some basis element b star, such that x is in that basis element, is a subset of this. So then we know this.
So I have a question.
Go ahead.
Why are you assuming x is in k plus 1, the intersection of k plus 1 for all those?
Because if x isn't in the intersection, then
It's vacuously true.
it's vacuously true. What are we trying to prove? We're trying to prove that if x is in the intersection of these basis elements, then there exists some other basis element such that x is in that other basis element, and it's a subset of their intersection. Sorry, I wrote down how the author had it instead of writing it the way that I like to write these. I try to always write these in if-then statements. If beta is a basis and b1 through bn are in beta such that x is in them, comma, then, okay, that's rewriting it as an implication, right? So we're trying to show that this implication is always true. When the antecedent is false, the implication is true, so ignore those cases. So now we only care about cases where the antecedent is true.
Okay.
So let x be something in there. We need to show that if x is in there, then there exists some basis element b prime such that x is in b prime is a subset of that whole thing. Right? That's ultimately where we need to get.
Yeah.
Okay. So let x be something in all there in the intersection of all the sets. So then x is in all these sets, the first k plus it's also in the k plus 1 set. Since x is in the intersection of k basis elements, there must exist some other basis element b star such that x is in that basis element is a subset of the intersection of the k basis elements. So now we know x is in b star and x is in b sub k plus 1. Right? So now everyone's good with line 3, ready to go to 4?
Yeah.
Yeah.
Okay. So now we know that x is in the intersection of two basis elements. By definition of a basis, then there must exist some b prime and beta such that x is in b prime is a subset of their intersection. Now notice that this intersection is just a subset of what we started with, right? Because b star is just a subset of this thing.
Which is just a subset of the other thing.
So we just took a smaller set and intersected it with the same set, which could only give us a smaller set, it can't give us a bigger set. So we for sure have a subset. So we found some b prime such that x is in b prime, and b prime is a subset of this, which is a subset of this. So we showed that the statement was true for 2. We showed that if the statement was true for k, then it was true for k plus 1. Therefore, it's true for all n greater than or equal to 2. For all natural numbers, all n in n, where n is greater than or equal to 2. Right? And that was our lemma, and that was our first proof by induction in this class. I don't know for sure, but I would bet a lot that there's going to be several more proofs by induction. So, make sure you get comfortable with it.
I'll try to.
Okay. Now, for the main event. Make sure I have my notes on the right page, just in case you need to reference it. Theorem 1.8. Theorem 1.8. Okay, it's right here. Alright. So let's prove this. So now we're going to prove the topology tau generated by beta is in fact a topology. So 1, what's the first thing we need to show?
You need to show that it has empty set and the set itself.
And the set itself. Right, so 1. Observe, how do I know the empty set's in there?
Because the empty set's in the basis.
It's not in the basis, but what did we say here? Let beta be a basis on x. Then tau, the topology generated by beta, is obtained by defining the open sets of tau to be the empty set, the members of beta, and the unions of the members of beta.
Okay.
So by
Right,
definition of tau,
Oh, so by definition
the
of tau,
empty
not
set is in
definition of
tau by def of a generated topology.
beta. Okay.
Good with that one?
Okay.
These definitions of theirs are confusing, because you said the topology generated, and now we're proving it as a topology.
I know, I don't like that the author talks about it as a topology before we proved it's topology. So, we talked about it like it's topology the whole time, now we're proving that that thing we always called a topology is in fact a topology.
So I'm confused. So you said you are proving that every single one of those that we said over there is in fact in a topology and it's not the word.
Say that again.
So now you said tau has to be the empty set or every set that is equal to or a union of the basis elements.
You're saying that wrong. If a set is the empty set, or it's a basis element, or it's a union of basis elements, then it's in tau. Tau is all the sets that satisfy one of those three conditions.
Okay.
A lot of things in tau.
Now we're proving that tau.
So for sure, all of beta is in tau, right? So
Yeah.
one thing we know for sure is that beta is a subset of tau,
Yes.
right? By definition of tau.
Yeah.
We know that the empty set is in tau for sure. Some basic things that we know.
Oh
Yeah.
no.
Okay.
All of these sets.
So now we need to say, so we know that the empty set's in tau. Now we need to say that x is in tau, right? The topology tau generated by a basis B on x, sorry I didn't specify my set x here, on x is a topology.
What
Sorry.
does it mean to be a basis on a set? Does that,
The same thing is, so back to our definition, let x be a set and beta be a collection of subsets of x, then beta is a basis for a topology on x.
okay.
So beta, let's see, better way to say it. Let the topology tau generated by basis beta, the topology tau generated by basis beta is a topology
On X.
on x. Still not about it. You get what we're saying, right? Okay, so we need to prove that x is in tau. How are we going to show that x is in tau?
Because of the union of basis elements.
We know that the union of basis elements is an open set, is in tau, but the union of which basis elements gives me x? Which basis elements do I use to get x?
All of them?
Yeah, don't
All of them? So you're telling me if I union up all the basis elements I get x?
Yes.
How do you know that?
Because it was defined, was it not?
You.
Look at the first thing that a basis has to do. For all x in x, there has to be a basis element containing that point.
Yeah.
2. Observe that for all x in big X, there exists some some basis element of x such that x is in Bx, right?
Okay.
Then the union, right out there, the union for all little x in big X of B sub x is equal to x,
Yeah.
which is in tau now. How do I know that the union of all those sets is big X?
Because it's for every x and big X. And there exists a basic basis that
Because
has
every
x.
x in big X
By
has a
the
basis
union
of-
lemma. Remember the union lemma? What was the union lemma? If I have a collection of, so if I have some set A, and I have a collection of subsets of A such that for every point x in A, there exists some set B around that point such that B is a subset of A. That's true for all the points.
Yeah.
Then the union of all those B's
Gets A.
then the union of all the b sub x's for all x in A is equal to A. That was the union lemma. That's what we proved in chapter 0, right?
Okay.
Okay, so we know that for every x, there has to be at least one basis element. There could be many, we just need to pick one. So for every little x and big X, there has to be some basis element that contains it. So union up all those basis elements, and you get the set X. We know that by the union lemma, and then since X can be expressed as a union of basis elements, it's in tau. Okay,
Yes.
so we showed that tau contains the empty set, and we showed that tau contains
X.
X. Now we need to show that the intersection of open sets is open. Right? We showed the first thing. So now we need to grab some finite number of open sets and look at their intersection and show that that is in fact open. Right?
Yeah.
Now what do I know about my open sets in this topology? Any of my open sets are either basis elements or unions of basis elements. So that's how we're going to have to prove it. We have to keep that in our mind. So we've done with the first step. So 4. Let U1, U2, UN be open. Alright, so we got finitely many open sets. Now we need to prove that their intersection is open. Right? So then the intersection from I equals 1 to n of U sub I. Let's see. Well, before we intersect them, maybe we want to explicitly say, observe that for each U sub I, we can express it as some union of basis elements. Let me think for a second. Let's just try it. Okay, so then for all U sub I, so for each of those open sets, comma, there exists, how do I want to write this so I don't make a mess of all that? I basically want to say there exists some set of basis elements whose union is that set, right? Oh, actually we've got two cases, sorry. One of those could be empty. So first let's take care of the case where one of them is empty. If any U sub I is equal to the empty set, comma, then the intersection from I equals 1 to n of U sub I is equal to the empty set is in tau.
Okay.
So if any one of them is the empty set, the intersection of all of them together is just the empty set, which is already in tau. So then, assume U sub I is not equal to the empty set for all, well, I'll just say for all U sub I, comma, U sub I is not equal to the empty set. Or just say, assume U sub I is not equal to the empty set. Basically what I said. For all I. Maybe you'd rather me do this. For all 1 less than or equal to I less than or equal to n. For all I, where I is just incrementing from 1 to n, right?
Okay.
Okay, so now assume none of them are empty. Now if it's not empty, it can be expressed as a union of basis elements. Right?
Yeah.
intersection can be expressed.
then each u sub I can be expressed as a union of basis elements, right?
Right.
Yes.
I've heard this before. Observe that if any, then that, so soon. Oh, I didn't use the union limit. Okay. Let u sub 1, let me write it smaller and plug it in here and name it. Let u1, comma, dot, 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 comma, u sub n in tau, comma, and let v equal their intersection. From I equals 1 to n of u sub I. It's just going to be useful to be able to talk about all that intersection without having to write over and over again.
Yeah, but you see, you said, oh, never mind.
So let u sub 1 through u sub n be open, and let v be their intersection. We're trying to prove v is open.
Yes.
So if any u sub I is equal to the empty set, then v is equal to the empty set is in tau. So now we're going to assume none of them, the u sub i's, are equal to the empty set. Now we're going to let x in v. How am I going to prove that v is open? I'm going to use a union lemma. I'm going to show that for every point in v, there exists some basis element containing that point that's a subset of v. With me so far?
Okay.
And so v, by the union lemma, is equal to the union of all those basis elements.
Yeah.
But then if v is a union of basis elements, it's open. Does that make sense, big picture, how we're attacking this?
Yes.
Okay. So, okay, so let x in v. What does that tell me? That tells me, that implies that x is in u sub I for every u sub I. With me so far?
Mm-hmm.
Now, what is each of those u sub i's? It's just a union of basis elements. It's just an open set, so it's a union of basis elements, one or more of them. It could be a basis element in itself, or it's a union of basis elements. But either way, if x is in a union of basis elements, then there has to be some basis element that x is in, because it's in the union of basis elements. So, then for all let me see how I want to say this. Then x in u sub I implies that there exists b sub I in beta such that x is in b sub I. If x is in some open set, and open sets, since we know none of these are the empty set, remember it's either an empty set or it's a union of basis elements. Counting a basis element as a union of basis elements, right?
Okay.
So if x is in an open set, then there must be some basis element containing it such that x is in that basis element, and that basis element is a subset of u sub I. And b sub I is a subset of u sub I. You with me?
Yes.
Because this b sub I is one of the basis elements that make up u sub I, in other words. Good? So then what do we have? Then x is in the intersection from I equals 1 to n of all those basis elements.
I'm not understanding.
So we're taking x is an element of V, but remember V is the intersection of all our open sets. Now for each of those open sets, x has to be in it, because x is in all of them. And those open sets are just unions of basis elements. So for each open set, there has to be a basis element that's a subset of that open set, such that x is in that basis element. It being a subset probably doesn't even matter. I don't think that matters, so get rid of that part. Alright, I got a period there. So 9, then x is in the intersection from I equals 1 to n of those basis elements. So for each u sub I, there exists a b sub I containing x. Pick all those b sub i's, x has to be in their intersection because it's in all of them.
Okay.
It seems like there could just be one b sub I.
It's the same basis element for every u sub I?
Yeah,
That's fine.
but you can't take the intersection of just one thing.
Well, then it's just that set,
Okay.
right? And I could write this if I want. I could write the AB intersect AB if I want. And it makes sense. So yeah, those don't have to be distinct basis elements. Could be the same basis element in all of them. That's fine.
Alright.
There just has to be some basis element. So then x is in the intersection of all those basis elements. Since x was in all those basis elements, what does that mean?
Then there exists beta prime, no, b prime in beta.
Perfect.
Yeah,
So then there exists some other basis element, b prime in beta, such that x is in b prime is a subset. Let me write it here because I'm going to write one more piece to it. Such that x is in b prime is a subset of the intersection from I equals 1 to n of b sub I. Right?
Yes.
And we know that this is a subset of v.
Yes.
You with me on that?
Okay.
Remember what v is. V is the intersection of all the open sets.
And we're trying to prove that B.
These are intersections of subsets of the open sets. And so they're still just going to be a subset, possibly the same set. It's possible that these are the same set, but this is for sure a subset of this. Right?
Yeah.
So what did we find? For each x, we found a b prime such that x is in b prime, and b prime is a subset of v.
Yes.
And if you can do that for every x in v, you can find a b prime such that this is true, then what?
And it's open.
Then using the union lemma, v is equal to all those b primes. We can call this b prime sub x if you want, so we know that that was a b prime for a particular x.
Oh,
Right? So we picked some point in x. What did we do? We found a basis element, b prime sub x, such that x is in that basis element, and that basis element is a subset of v. We can do that for every point in v. So for every point in v, here's v. pick a point in there, x. We found a basis element, b prime sub x, such that x is in b prime sub x, and b prime sub x is a subset of b. We showed how you can do that for any x you pick. Pick any point in b you want, we can find the basis element that captures it. Therefore, the union of those basis elements is v, by the union limit. So 10, then v is equal to the union for all little x and big X of b prime sub x, which gives us that v is in our topology. Anything weird there? Do we just need to say it again?
Yeah.
Did we lose track of what we're doing?
No, I got myself confused on line 9 again.
On line 9. Okay.
I just, it looks like you're saying x is in each one of the basis elements.
X is in every one of these basis elements.
So what are you saying?
So all of the basis elements.
No. So what did we start with? We start out with an open set. So we have a bunch of open sets, and what do we know about? Maybe try and draw a picture. So we start out with a bunch of open sets that we know intersect. So a finite number of open sets, has to be finite. So U1, U2, U3. We'll try and keep it simple. But obviously we just need n of them that all intersect. We are saying pick some point in their intersection, x. Here's x. Since U1 is just a union of basis elements, then there has to be some basis element that makes up U1 containing x. We'll say that that happened to be, we'll just split it into half. So divide it into half, boom. This half down here is B1. We'll try and draw it up here. B1. I know that's not really half, but. Okay, let's pretend that all these were a basis element. With me so far? And then over here, we'll cut it right there, and we'll say all these were a basis element B2, and then we'll cut this one right here and say all these over here were a basis element B3. So now we have x is in the intersection of finitely many basis elements.
Okay, I'm just, how do you know that that finite number is the same finite number that you chose for the number?
It could be repeating basis elements. So this is one possible picture. The other way we could have had it is U1, U2, U3, here's x, and B1 is this, B2 is that, and B3 is that. And they're all just that little subset around x. That's a possible picture, here's a possible picture.
Right, in that there's just one basis element that we're trying to talk about.
Right, so we are taking that B sub 1 intersected with B sub 2 intersected with B sub 3. In this case, they all happen to be equal. In this case, they're not equal. But what do we know for sure? Whatever this intersection is a subset of the intersection of U1, U2, and U3.
Okay, I think I understand now. So is it because you call B sub I the basis element of U sub I that contains x?
Yes,
Okay.
that's exactly what B sub I is.
Alright,
B sub I is a basis element that makes up U sub I that contains x. It's exactly what it is.
that makes more
Okay.
sense where you're getting each B sub I then.
Okay,
And why the
yes,
same finite number.
perfect. Yeah, it's a very dense notation, easy to get lost in it. Talk about it's a lot of abstraction. Okay, so what did we show? So now we know that x is in the intersection of finitely many basis elements. Using this lemma over here, that means that there has to be some other basis element that is a subset of their intersection containing the point. And this is our b prime x. B prime sub x. Over here, it might have been exactly the same thing that all those basis elements happen to be. So here's two very extreme cases. So in this case, b prime sub x is equal to the intersection of all these. In this case, it's definitely something different than the intersection of all these. In either way, it's definitely a subset of their intersection. Right? So now we're saying for any point in their intersection, that happened to be the case. We just picked one point x. You can do that for any point x in all their intersection. V is this set right here. It's the set of their intersection. It's this. Right? Since for every point in V we can do this process, then for every point in V there exists some basis element, b prime sub x, such that x is in b prime sub x, and b prime sub x is a subset of V. So then by the union lemma, all those b prime sub x's unioned up together gives you V.
And does that prove point 2 of proving a topology?
Yes. What was V?
V was intersection of all open sets.
V was an intersection of finitely many open sets.
Yeah.
Which ones? We don't know. Just pick any finite number that you want, and we show that its intersection is also open. Any questions there?
Are you saying we're done proving 2?
No.
Yeah, we're done with case 2. So we've done case 1 and case 2. All that remains is case 3, which is really easy.
So is it true that there's always a point in V? You said let x in V. Do we need to take the case where there's not anything in V, or is that never the case?
Where their intersection is empty.
Where V is empty?
If V is empty, we already showed that the empty set is in there.
Well, that was if one of the UIs was empty. I don't think that's technically the same thing.
No, it's not. But we need to show that if x is in V, then there exists some subset of V containing it. That's what the union lemma did. So to satisfy the antecedent of the union lemma, we need it to be in there. And we know that if this isn't satisfied, then it's vacuously true. If V is empty.
Okay.
Because then the only subset of V is the empty set. Well, the union lemma, what does the union lemma say? If for every point in V you can find a subset, well, if V is empty, there are no points in V. So it satisfies the union lemma vacuously. That's probably the right way to think about it. Okay. Any other questions on that one? So now we need to prove the third one. What's the third one? That any union of open sets is open. Right?
Yeah.
And all our open sets are just unions of basis elements. So when we union up unions of basis elements, we're left with a union of basis elements, which is going to be open.
Right.
Right? Now we need to handle the case where they're all empty. So 11. Okay. Let's just see how I write it here so that we don't take more lines than we need. How would you use that? Use 5? We'll squish it. 11.
Tony, you're not supposed to be that one person who squishes all their writing onto their page.
That's when you're using paper, where you have so much of it, it's absurd to not go to the next sheet. Here we've got finite real estate. I can't just extend my whiteboard. All I can do is erase. Alright, we'll be fine. By the way, you just dropped a letter grade in this class. Alright.
Thanks.
That means you get a grade? What? Now let V equal the union. V equal the union of some arbitrary collection of use of alphas, where use of alpha is just an arbitrary open set. So we've got some collection, some arbitrary collection of open sets. Could be infinite, could be finite, could be one thing in there, who knows. Union them all up, that's what V is. With me?
Mm-hmm.
So now we just need to show that V is open. 12. If every use of alpha is equal to the empty set, then V is equal to the empty set, which we already showed is in the topology. 13. Now assume that there exists some use of A, I'll call it, in our arbitrary collection of open sets, such that use of A is not empty. So either all the sets are empty, or at least one of them is not empty. Call the one that we know for sure isn't empty use of A.
Okay.
With me so far? So then use of A is going to be, well, let's just keep writing that right here in case I take too many words. Assume some use of alpha is not empty, then it is a union of basis elements. Then V equal to that is a union of basis. Oh, this isn't the proof I had in mind where we need to specify this. Sorry. I know I had to do that on the proof, but for some reason I thought it was this. So, what's the right way to say this? Assume use of alpha is not empty. Assume some of them are not empty. Assume some use of alpha are not empty. Could be one more. Are not empty. Then they are a union of basis elements. And I won't bother writing an abstraction. We just say for each use of alpha, let be 1 sub alpha, 2 sub alpha, 3 sub alpha, 4 sub alpha, be all the ones for a particular alpha, union them all up. If we won't do it that way, we'll just skip to keep the notation cleaner, and because I'm running out of space. Then V equal to the union of all those use of alphas is a union of open set, is a union of basis elements. Is a union of basis elements, which gives us that V is in T, and we're done. Right? I didn't explicitly write out all the basis elements that we're unioning up and showing that a union of unions is the same thing as a union of just the elements themselves.
Yes.
But I think you would know how to do that if you want to. And I think you understand the idea. It's a pretty straightforward idea on unions. It's the intersection that is tricky on this proof. And you can read how the book does it. For those of you that don't have the book. You have the book. The rest of you don't. Okay. How are we doing? You feel like you got the brain power to keep going? Or was this too much?
That was a lot.
That was a lot? We're not going to get through this whole section in one day, I didn't think. There's still more after this. Maybe we'll skip this here. It's a small theorem, but maybe we'll skip it, and this will be like a good come back to recapture this. But I want to go over this stuff with you real quick. Just because it's not really topology stuff, it's just some basic definitions and maybe some geometry in case you guys don't have it yet. So we'll just look at that stuff, and then we'll call it. So, consider the plane R2. I mean, it all makes sense to us now how R2 could be used to represent the plane, right?
Yeah.
What's R2?
It's just
Two-dimensional.
What exactly is R2? It's the set of all possible ordered pairs of real numbers. It's R crossed with R. R2.
Yeah.
Okay. So consider the plane R2, the set of all possible ordered pairs of real numbers. Now we're going to look at 2 points in R2. P, which we'll represent with P1 and P2, and Q, which we represent with Q1 and Q2. Then the distance from P to Q is this formula. How many of you are comfortable with this formula? Who isn't comfortable with this formula? You're not comfortable with the formula.
No, I'm not.
Okay, then let's go over the formula. Are you comfortable with the Pythagorean Theorem?
Yeah.
You know how it works. You can prove it.
I don't think I can prove it.
Let's go to the Pythagorean Theorem then.
Okay.
It's nice and easy. We're just going to do a quick geometric proof that's not very rigorous, but you'll see the idea on how it works. So I'm going to create 2 squares here. I'm going to need some space to write on your room, so up it a little. So square and square. Now I'm going to break this up into A, B, and break this up into A, B. So the area of this square right here is A plus B squared, right?
Yeah.
That's the area of that square, which is, if you break it up geometrically instead of looking at the algebra, here's A squared, here's B squared, here's AB, here's AB. So it's A squared plus 2AB plus B squared. Kind of cheating and using some algebra in our proof. I just want you to get the idea that we're not rigorously doing geometry. Now I'm going to write the same square, but I'm going to draw it a little bit different. So this is A, this is B, this is B, this is A, so the square is still obviously A squared plus B squared, right?
Yeah.
B, A, B, A, and then connect the lines like this. Doot, 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 doot. Now we know that these are all right angles, right?
Mm-hmm.
I'm going to call the length of this side C, 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 C. So we've got an internal square with sides C, right? So, what's the area of this thing?
A plus B squared.
What's the area of this triangle? So we're going to calculate the area of this thing. This is 1/2 base times height. 1/2 AB, that's the area of a right triangle. But we have 4 of those. And then we have the square in the middle, C squared. That's this, right?
Mm-hmm.
Yeah.
Or in other words, we have 2AB plus C squared. So A squared plus 2AB plus B squared is the same thing as 2AB plus C squared. Subtract 2AB from both sides, A squared plus B squared equals C squared. Nice, simple proof.
Okay.
So that's Pythagorean Theorem. So that's how we can calculate how long C is if we know A and B for right triangles, right? Now, when we're talking about in the plane, what do we mean by the distance between 2 points? Get rid of that since we're not using it anymore. So if I've got a point P here, and I've got a point Q here, the distance is, when I say the distance between those 2 points, I mean the length of this thing right here, right?
Yeah.
Now, I could just, in my brain, create a right triangle where that's the hypotenuse, right? No reason I can't do that.
Okay.
Now I'm going to draw this on a coordinate system to help us think about it. So here's my y-axis, here's my x-axis. This point right here is P1. Remember, P1 is the same thing, or P is the same thing as P1, comma P2.
Yeah.
And this is Q1, comma Q2. Right? So that means the x-coordinate here is P1, and the y-coordinate here is P2. The x-coordinate here is Q1, and the y-coordinate here is Q2. You with me so far?
Yeah.
Now, what am I trying to do? I'm trying to calculate this length. Now, what do I know? I know that this length squared is equal to this length squared plus this length squared, right?
Yeah.
Yeah.
So I need to find these two lengths. But what is this length?
P1 plus Q1.
The distance between P2 and Q1.
How do I find the distance between Q1 and P1?
Oh.
Q1 minus P1.
Q1 minus P1.
Yeah.
What's the difference between, or what's the distance between 10 and 7?
3.
3. How'd you do that, magic
Yeah,
math?
sorry.
All right, so this distance right here is Q1 minus P1. And this distance right here is,
Q2 minus
Q2
P2.
minus P2.
getting better, Q2 minus P2. Okay, so now I know that, and we're going to call this length here C, just for the sake of we're using Pythagorean Theorem. No, let's keep track. Or actually, we'll call it D of P1, D from P to Q, right? Because that's what we're saying. We're going to call this distance,
Yeah.
the distance from P to Q. So I know that the distance from P to Q squared is equal to this squared, Q1 minus P1 squared, plus Q2 minus P2 squared, right?
Yes.
If I square root both sides, it's always positive numbers. Square root of positive number is just positive number. Square root both sides, I get D from P to Q is equal to the square root of P1 minus Q1 squared plus, I wrote that backwards,
Yeah, you mean Q1 minus P1.
Q1 minus P1. Doesn't matter the order, but we'll be consistent for a second here. Q1 minus P1 squared plus Q2 minus P2 squared, right?
Mm-hmm.
That's how we got this formula. Almost. There's one technicality that we didn't account for. When I said what's the distance between 10 and 7, you did the bigger one minus the smaller one. Now we don't want to have to keep track which one's bigger, which one's smaller. So what's the distance between two numbers A and B? If I don't know which one's bigger, which one's smaller, how do I describe their distance?
The
Absolute value.
Absolute value of A minus B. That's their distance. So it's really the absolute value of this squared, and that way we don't have to keep track of which is which, and the absolute value of this squared.
Okay.
But when I take the absolute value and I square it, that's the same thing as just squaring it.
Yeah.
Because a negative squared is positive, a positive squared is positive. You get the same number either way. So we don't need to keep track of that. So it doesn't matter if I did Q1 minus P1 or P1 minus Q1. I'm going to get the same thing when I square it.
Right.
Okay.
3 squared is 9. Negative 3 squared is 9. Okay, so that's where this distance formula comes from.
Okay.
Alright, so consider the plane R2. For 2 points P and Q, the distance from P to Q, or from Q to P, however you want to think about it, it's the same distance, it's always a positive number, is this formula, the distance formula. The Euclidean distance formula. Now, we're going to move on to another definition. For each x in R2, what is x?
A point.
A point. It's not a number, it's a point. For each x in R2, and for any positive number epsilon you choose, we're going to define the set B of x epsilon. This is going to be notation for a set. What's it going to be? I'm going to give you the intuition first and we'll read exactly what it says. This is going to be a ball of all the points centered at x with radius epsilon. It's going to be a ball that looks like this. It's going to be all the points in this ball. So take a ball centered at x with radius epsilon. Now take all the points inside that ball, not including the border.
When you say ball, I picture 3D art.
So we're going to call this a two-dimensional ball, and we're going to have a three-dimensional ball, we're going to have a four-dimensional ball, and we're going to give them similar definitions.
Like what?
Right.
And our one-dimensional ball is just an open interval.
They're just completely.
So ball is no longer a three-dimensional thing.
Okay.
Ball is all the points within some distance of a point. That's what we mean by a ball. So in two-dimensional, we're talking about a plane. If I were to look at all the points within a foot of this point in 3D space, that would give us a sphere of radius 1 foot, right? And it's obvious how it looks in 4 dimensions, right?
Yeah.
Okay. So yeah, we're going to not use ball in the most intuitive way. Right. Okay, so the ball centered at x with radius epsilon is equal to the set of all points whose distance from x is less than epsilon.
Okay.
So we don't include the border. Why don't we include the border? Because their distance is exactly epsilon from x. We need their distance to be less than epsilon from x. So we don't just call it a ball, we call it an open ball. An open ball means it doesn't include its
Doesn't have a
border.
border.
If it includes its border, we call it a closed ball. An open ball in 1 dimension, we call an open interval. And a closed ball in 2 dimensions, we call a closed interval.
Okay.
Okay, so you good with what this set is? Okay. Then, the set, oh, that is called an open ball of radius epsilon centered at x. Okay. Now let beta be the set of all possible open balls.
Okay.
That is a basis for the standard topology on R2.
Oh.
That's kind of cool.
That's going to be our standard topology on R2. Notice it's identical to our topology on R when you make it a one-dimensional thing.
Oh.
An open interval is just all the points within half the interval of the middle point.
Oh, are you saying that the basis is all the
open
All the-
balls.
Every possible open ball you can make.
okay?
That's our basis.
But each one has a different epsilon, right?
Yeah, just like we can have different lengths of intervals.
Okay, I thought
So the standard topology on R was the basis for the standard topology on R was every possible open interval. Some small, some big, any open interval you can make anywhere. That was our basis elements. What's our basis elements on R2? Any open ball you can make anywhere. That's a basis element. And any set that can be represented as a union of open balls is an open set. So let's do a quick example to help make sense of this. So let's say I'm taking the whole xy plane, I'm going to draw a square to we're going to draw it in here. But what happens if I were to take all the points to the left over here? Is this set open?
Yeah.
Let me try this one more time. Maybe it'd be better if we had a coordinate system to help us think that we're in the xy plane. So I got some coordinate system we were talking about in the plane. Now I've got some dotted line, and we're talking about the half plane over here. All the points over here. Is that an open set?
Yes, I think so.
Yeah. Let's think about another one. What about if we did that and we did all the points over here as well,
Yeah.
but just not the middle strip?
Yeah,
Yeah.
it's still open.
Okay, and then what about if we also included all the points up here now? So now we're just missing that little rectangle.
Yeah.
Yeah, and then what if we come down to the bottom here and include all these, so now we're just missing that square?
Yes?
Yes. What about if we just had all the points in this square, not including the border, but none of these other points?
Yeah.
Yeah? Yeah. Your intuition's right. Let's try a really crazy one. What happens if I have all the points in R2 except for that point? We're only missing one point. I go to R2 and I pluck a hole out of it. I just take...
Yes, that is true.
That's open?
Yes.
Yeah, then we do it.
Because we did it in that one.
Yeah.
Yes, that's open. Okay, so feel like you got some basic understanding of some standard topologies. We did the big one, what a basis is, how a basis generates, and we proved that the basis is a topology. So that was a good start, and we'll finish the rest of the stuff for basis elements next time.
The basis is a topology.
How a basis generates a topology is what I meant to say. I'm not sure what I said. We said what a basis is, the topology a basis generates, and then we proved that the topology it generates is a topology, even though we called it a topology before we proved it. Any questions? And whatever that theorem is I erased, that's what we're starting next time to hopefully try and pull some of this back into us. But even if you don't exactly understand the proof, hopefully what we proved makes sense to you. You can remember what we proved. What did we prove? That the topology a basis generates is a topology. Think you can remember that?
Yes.
So if I put a question on the test, is a topology that a basis generates a topology? You now know yes.
Yes.
So you'll
or
remember
no.
it. Yes or not yes?
That is true. Yes.
Yeah, you want